So I'll be talking about a specific example that we've been using deep learning to do a classification problem that's a big issue in what's called time domain astronomy right now. I think the focus of my talk will largely be from the perspective of an astronomer learning data science, how I'm making those human decisions of where to grab off the shelf tools and what tools I chose versus building our own. And in none of these cases am I building a neural net in C++. All of them are using Python. So some scientific context. So time domain astrophysics is the study of variable things in the night sky. What's fun is that there's a lot of high energy physics that you can actually study in this discipline. So for example, stars can have kind of these final terminal moments of their lives that can end in eruptions, explosions, and collisions. And so I'm showing you some pretty pictures here to illustrate that. So for example, a star can get too close to a black hole and be disrupted due to tidal forces, and we watch that disruption as shock physics. Or we can have two neutron stars collide and we watch that collision in gravitation, or I guess we hear that collision in gravitational waves, and then we can watch the very heavy or R process nucleosynthesis as it happens and understand that final physical processes there. So that's kind of the idea, is how do we take the observables that we briefly get from the night sky and then translate it into this kind of zoo of astrophysics. So just very briefly, what does the data actually look like? So in reality, we take these nice pictures like the movie I'm showing you, where we look at other galaxies outside of our own, and we see new sources of light, which are typically a star dying in some dramatic fashion, which I'll just generically refer to as a supernova. And these are visible for kind of days to months. And in that time, ideally, to study the physics, we would like to grab every photon at every wavelength at every point in time. The reality is that doing spectroscopy on these objects is very expensive because you have to build up significant signal to noise in very small photon bins. But here I'm showing you theoretically what something like that type of movie would look like, where this spectrum is evolving in time. And you can see there's kind of an overall shape, which tells us about the bulk properties of the black body emission. So we can understand kind of the energy involved and the mass of the star that exploded. And then on top of that, we see these little wiggles, which are spectroscopic signatures of individual elements. And so then we can use those to kind of probe, okay, exactly what's being synthesized or exactly what was present in the outer layers of the star. So we ideally want to do both to loosely classify into the underlying physics. But because it's so expensive, what we actually end up doing is we take broadband filters and kind of convolve over this spectrum. And instead we get something called a light curve, which is plotting as a function of time the integral of part of this spectral energy distribution over time. And they have roughly this kind of shape that I'm highlighting. So they get brighter and dimmer and they change colors. So we're going to use those inexpensive light curves to understand the underlying physics, or at least get a snapshot via classification problems. The reality is not that pretty. So this is a real now light curve of something that is spectroscopically being classified as something called a type 1A. So the different colors represent the different broadband filter colors, which you can see often are not observed on the same night. So it's kind of a sparse light curve, but in terms of coverage, we get most of the light curve over the 30 days that's visible. So this is our problem, is that now we deal with kind of these irregular, sparse and noisy light curves to get the underlying physics. So this problem is getting worse or better, depending how you look at it, thanks to a new observatory that's coming online in 2022 that's called the Rubin Observatory. So this is a histogram of the number of supernovae we discover each year. And this is a silly GIF that shows that Rubin is going to increase this discovery rate by 2 orders of magnitude. So well over 1 million supernovae will be discovered. With that, we're not going to increase our spectroscopic resources. And unfortunately, the vast majority of classification techniques right now rely on having at least one spectrum. So right now we only get spectra, so a classification of about 10% of all events. And that will, because that number is not increasing, the fraction of supernovae, which will have spectroscopic information for the Vera Rubin Observatory, will be just 0.1%. And so right now, the state of the field is that we actually just ignore, basically, the 90% where we don't get a spectrum. We don't do any science with it for the most part. And that's partially because we have enough on our hands with the 10%. But suddenly, when we have now 1 million objects and only 0.1 getting spectra, it's not advantageous to throw away 99.9% of our data. So we need these new methods to take the light curves directly, make some statement, and then decide whether or not we want to actively study that object or let it sit for statistical population level studies later on. And so that's loosely what I consider to be this needle in a haystack problem that the Vera Rubin Observatory is going to hand to time domain astronomy. So the haystack is the million or so events that will receive no human hours to them until probably well after the survey has completed. Of those, like I said, several thousand might get a traditional label associated with them. But amongst those, maybe 100 per year will have human hours actually devoted to them in real time, where we trigger multi-wavelength observations to get a full idea of the underlying physics. And so to me, these 100 or so, which is, so 100 in a million, it's about a 1 in 10,000 level of quote unquote importance, of scientific importance, that we need to decide on in real time and then follow up. Those are the needles to me that you need to actively find. And obviously, I believe that the way to do that is through data-driven methods. In particular, I want to talk about what I consider to be the rarest kind of needles, which are the unknown unknowns, or the anomalous events that we can't expect or we cannot predict with our current knowledge. So some either new physics or astrophysics that Vera Rubin will see, but we don't know whether or not we will know that we should trigger on it in real time. So the way we approach this problem is through an unsupervised anomaly detection algorithm that relies on a variational recurrent autoencoder, which I will go through basically step by step. On this slide, I will just point out that the unsupervised portion is due to the fact that our current observational data set, the training set we work with, is a biased representation of the true night sky. And that is because there's never been a data collection of this caliber before. And so it's important to, in one way to not bake in some biases, is to have a completely unsupervised look and not rely on known labels, especially if we're looking for the unknown unknowns. Okay, so there are basically 3 steps to our algorithm. The first is that we will do pre-processing. The second is that we will train our autoencoder. And the third is that we will look for the weirdos or the needles. So in the first step, like I mentioned, we have these irregularly sampled multi-band time series. And for that, I tried a number of, so we want something to be able to handle live streaming data. And the natural kind of solution there is, okay, use a recurrent type of neuron so that every time you receive a new data point, it can be updated somehow, feature extraction. But then there's a question of what do you do with missing data amongst the different bands? And for that, we decide to use Gaussian processes, which is a typical technique in astronomy. So we choose to do this so that at every point in time, we can have all n bands. And the way we do this is actually with a really wonderful Gaussian process package that was developed by Dan Foreman-Mackey at the CCA, which is called George, and then the much faster version Celerite, which are both pip installable. And what's useful about, well, The way we use this is we use a 2D kernel. So we specifically want to entangle or correlate both a time correlation temporally and then a wavelength correlation. So the idea that we know there's some underlying function that's a spectral energy distribution with time. And so all of these n bands should know about one another. And we do this by actually looking at the overlap of the filter functions of the broadband filters that we use. And the more they overlap, the more we expect them to be correlated. Okay, so then the next step is we learn the encodings using a, like I said, a variational recurrent autoencoder. This is generally the picture here, where now we have very dense input matrices, which are n multiband filters versus kind of m time steps. We feed these in along with the Gaussian process errors into a somewhat standard autoencoder with one trick. So, well, I guess two. First, we use recurrent neurons, which just really briefly, a recurrent neuron is, so there was a nice explanation of kind of convolutional neurons in the last talk. These are also simple to understand. It's the idea that you want a nonlinear function or some state that remembers the previous state of your input data. And so this can be something as simple as just combine the two through combine the previous observation and current observation in some nonlinear function to make the next decision. Or there are slightly more advanced techniques. So we use gated recurrent units in particular, where instead you try to combine previous observations, current observation, to understand what's information I should forget versus remember in order to inform what the next kind of decision looks like. Okay, so all of these neurons are recurrent. So then what an autoencoder does is it just asks the question, given my input time series, can I return to you the same time series, which is a very straightforward question to answer. And we do this with a really simple, just least squares regression loss function. But in that process, of course, there is a bottleneck of information where the autoencoder must return the same time series, but only given a very small vector in the encoding, kind of the middle state. So from 10 numbers or something, completely reproduce the light curve of several hundred values. This is very similar to, well, for my intuition, it was easy to understand this as kind of learning a function in which physically I would understand a function that loosely, that can model something like the energy of my supernova and the mass of it. But here I'm just saying, well, I don't know the functional form, but I know that you can probably get to it with a series of nonlinear combinations and roughly 10 free parameters. And that's what's defining the encoding layer. So then what we actually do is for every time in the time series, we repeat the encoded layer n times, and we append to the encoded layer the value of that time relative to the maximum time of the flux. So in other words, I'm saying every time, okay, the encoding layer is going to give me back the light curve, but I specifically want the value of the light curve at time 0. Okay, now at time 1, at time 2. So in practice, we ask for it to give us back the encoding, or sorry, to give us back the light curve at exactly the times we feed in so that we can minimize the loss. But then it turns out after this training is done, it works like an interpolation or an extrapolation of a function because we're able to call this neural network model at any time we want. So I can kind of show this in practice how it works. So this is an example real light curve that spectroscopically, so I know the answer. It's a type 1a, which is a very normal explosion for us. And what I'm going to show you is based on the real data I'm showing this trained neural net, what does it think that the supernova will do in the future? So there's a lot of astronomer intuition here. So my intuition tells me right away, this is not quite right. It's something that is quite dim and short-lived with just a little bit of data. But what's interesting is that given just a few more days of data, very quickly the autoencoder picks up, oh yeah, this is probably something that will peak at roughly -19, which again, to my eyes is correct. I know that type 1As always have roughly the same luminosity, and that's actually why they make great standard candles for measuring distances in the cosmos. And then just a few days after that, it picks up on another kind of interesting signature of type 1As, which is that the redder bands have these kind of extra bumps due to probably some opacity effect. So that's exciting. It seems like it has picked up on a lot of subtle physical components of these models that I otherwise have not coded in. And just to show kind of the final output. Okay, but that's not the job. The job is not to reproduce these light curves. In the end, I want to find the unknown unknowns. I want to find things that look different than everything else I have fed to the neural network. So for the last step, we use an isolation forest to look for outliers inside the encoding space of our autoencoder. And so the way this works is that we basically, through a series of decision trees, we try to separate all of the ensemble of different supernovae in the training set. We try to cluster them out. And the idea is that outliers, or things which are kind of out of distribution, will be very easy to remove from the distribution through a series of decision trees. So in general, they will have kind of the shortest length to become separated. And so what this does, what the isolation forest does, is it just measures how long does it take this example to be separated from the group, to be singled out. And then you kind of use the inverse of that to write down an anomaly score for every single event. So this is what we do in the encoding space using this really wonderful simulated data set of supernovae called Plastic, which simulates 3 million supernovae, just as, well, hopefully just as they will be observed in the Villar Rubin Observatory, with the idea that we want to try to find either with the idea that we've actually in that simulation labeled the underlying physics. And so we want to find things that are in fact anomalous by some physical means. So we know that they are a rare class, or they are a class that have not been observed before, but have been included in the simulation as a theoretical possibility. So like I said, we searched the encoding space for these anomalies using this isolation forest. And what's nice about the variational part of the autoencoder, which just attempts to, instead of encoding every object, it tries to find a distribution for every object, which helps just kind of makes every object form a nice distribution. They're being selected from a distribution you define. So in this case, a multivariate Gaussian. And then we use the isolation forest to find the anomalous events. So what's useful about this repeat layer and the fact that it's recurrent now is that at every time in the evolution, we can ask the question, what is the anomaly score relative to all other events? And so here I'm showing you an example of, from this simulation, a rare class of supernova that's called a superluminous supernova, which is a great name. It's a class that, like it sounds, it's very bright, and we believe that under the hood, it's being powered by a newly born magnetar, which is a highly magnetized neutron star. So these, in my eyes, would be an exciting anomaly, something that people would want to trigger a telescope on. And what's interesting is that we can, I'm showing this middle panel, tracking the when it does not become an anomalous event, where anomalous means in the 15,000 or so events that we were training on, when does it reach the top 0.5% of anomaly scores? And so that happens notably before peak, which is really exciting for astronomers because often a lot of the interesting physics happens very early on and then it decays away quite quickly. And then what we can also do is watch as the event evolves in encoded space. So here I'm showing you time is represented. So all these purple points are showing this particular event in the distribution of all events, where purpleness is corresponding to time. So you can kind of watch it drift out of the main distribution. So right now what we're thinking about are ways to connect the physics that we care about to have some useful metric for actually determining how well this anomaly detection algorithm is working. That's kind of hard because there's a lot of philosophical questions on what is interesting. Yeah, I think I will end there, and I'm happy to take questions.